Now today we're going to be doing a related rates problem. Related rates problems are usually quite tricky. Usually your intermediate or even your advanced calculus student will have some difficulty with it just due to the intricacy of the problem and how many variables are involved in solving it. Now, a typical related rates problem that you'll see is one involving a conical section. In this case, it involves a conical tank and water is being filled into the conical tank. The problem is one I took off of the internet, and that it says that a conical tank is being filled at a rate of 2 cubic feet per minute. The radius of the conical tank at the top is 4 feet. The height of the conical tank is 10 feet. And find the rate at which the water level or the depth is increasing when the depth is at 5 feet. So let's work this out together and make sure we understand what is being asked. So here's my conical tank. And the first thing I said is that water is going into the tank. So let's draw our water coming into the tank right over here, filling up my tank slowly. And it's going to fill from the bottom all the way up to the top. So let's say after a few minutes, maybe my water level is right over here. And then maybe after another few more minutes, the water level might go up to here. So the water level is rising in my tank. The change in the volume of the tank over time is 2 feet cubed per minute. How do we know that? So it says that the tank is being filled at 2 cubic feet per minute. When anything is being filled, you're always talking about an area or a volume. In this case, it's a volume. How do we know that? Because it's a conical tank, a cone. A cone is a three-dimensional object, so when you fill a three-dimensional object, you're filling its volume. So the change in the volume of the tank is 2 feet cubed per minute. So if we remember calculus here, this little d means change. So the change in the volume over the change in the time is equal to 2 feet cubed per minute. The change in the volume, 2 feet cubed, so it's changing by 2 feet cubed, divided by the change in the time, divided by 1 minute. Find dh dt. Now h I labeled as the height of my cone, and r I labeled as the radius. So if you could see that cone is being made up of circles, there are layers one after the other from the very, very bottom tip all the way up to the top, and that forms the last layer of circles. So the radius of the very, very top circle is equal to 4 feet. The height or the depth of the whole entire cone is equal to 10 feet. And I label these capital R and capital H because they do not change. They are constants. The radius will always be 4 feet at the top, and it will always be 10 feet because the cone is 10 feet tall. What it's asking you is to find how fast the water level is rising. So let's say the water level is over here a second ago. Now the water level is going to go all the way up to here a few moments later. So what happens in terms of how fast the water level is rising when the height or the depth is exactly at 5 feet, exactly half of my overall 10 feet for the cone? That's what the question is asking. Find the change in height, dh, over the change in time. So how fast is the height changing over time when the height or the depth is 5 feet. Now to solve this, we need to set up some geometry and similar triangles. The problem with this is that you'll see that there's too many variables being involved. The key formula for solving this, let me switch colors, is the formula for the volume of a cone. You need to know that to be able to do this, and it's V is equal to 1/3 pi r squared h. You need to memorize these formulas, certainly the one for a cone, for a sphere. Some of the other ones are easier to memorize, but these are the ones you definitely need to know. For a cube, I would know as well. What do we need to know now? So now we're going to differentiate this. The problem is if we differentiate, we're differentiating always with related rates with respect to time. So dv dt. That means that you need to do some product rule for this one over here, which will make it very, very messy. The simpler way is to find some type of relation between my little r and my little h so that I can knock out one of the variables through a substitution and be able to solve dv/dt directly for dh/dt. How do I do that? So what you'll need to do here is think of my cone as a series of triangles, right triangles. So you might have one triangle going straight up over here. Okay? And then another triangle might be down over here. These are right triangles. So let me redraw this in case you don't see it so well in the cone. So here's my first triangle, right triangle right over here, and then I could draw another triangle with a right triangle right over here. Okay. So what happens with these two triangles is that they are similar triangles. How do we know that they're similar triangles? We know that all three angles of the little triangle that's over here and the big triangle over here are exactly the same. How do we know that? We have a right angle over here that's 90 degrees, and we have a right angle over here that's also 90 degrees. So that one works. We have over here in the bottom an angle that's being shared by both triangles, so obviously it's the same angle as well. So if these angles are the same and this angle is the same for both of them, obviously the third angle here and here is also the same for both triangles. So from that, we know that the two triangles are similar. Next thing I'm going to do is label the sides. So over here, I'm going to label this little h, and I'm going to label this big leg over here capital H. Same thing with the radiuses. I'll label the big leg capital R and the small leg little r. And you'll see that this mirrors what's going on in my conical tank over here. So the whole height of the tank over here, that's the big leg over here, is capital H. It's the same H that we have over here. It's our 10 feet. And the big R over here is the radius at the very, very top, and that's my 4 feet. I could make another triangle anywhere along the way that involves a little h and a little r. And what we could do is set up a ratio between the big H and the big R and the little h and the little r. Here's the ratio. If you remember this from geometry, the ratio of one side of the one triangle to the same side of the other triangle is equal to the ratio of the smaller triangle to the same side again of the bigger triangle. Little h over big H is equal to little r over big R. So luckily for us, we've already put down some of these numbers up top, so we could substitute and solve. Little h, which is unknown, that's our height at some certain point in the conical tank, over big H, that's the height of the whole tank, we know that's 10 feet, is equal to little r, that's 4, over little r, which is unknown. Sorry, let me erase that. That's our unknown variable, over our big R, okay, little r, over our big R, which is 4 feet. Okay, so those are our ratios. Somewhere there's a little triangle with H, somewhere there's a little triangle with a radius of R, and then our big triangle with a height of 10, and our big triangle with a radius of 4. Now we can cross multiply and solve for this. We're going to get 4h is equal to 10r. Last step is we need to solve for one or the other. So we need to solve for one or the other and put it into our generic volume formula up here. Which one are we going to solve for? Well, the problem is asking you to find dh/dt. So we need to solve for r, so we can input the number for r and get rid of the r, so it's going to be v and h as our only variables. So let's solve for r. We're going to divide both sides here by 10. Divide this by 10, divide this by 10, and we get a final answer that r is equal to 4/10 h. Alright, now we're ready to work up the final problem. So let's do this in a different color. Let's do it over in maybe green. And we're going to substitute the number we just did. That substitution is key to being able to do this problem well and fast. So v is equal to 1/3 pi, but now instead of r, I'm going to be using my 4/10 h, and then this whole thing is squared and then times h, right? So basically I have my r squared at the top here, my r squared at the top here, and this is the same exact little r we have at the bottom over here. So all I did was put in 4/10 h, and I'm squaring the whole thing because that r is squared as well. Okay, so now it becomes a question of algebra and simplifying. 1/3 pi, okay, and then we're going to do this part as well. When we square the 4/10, remember in a fraction, when you square it, you square the top and the bottom. So 4 squared is 16, and 10 squared is 100. Okay, and then h is also becomes squared, but I'm going to multiply it by that third h outside here, so we have an h cubed. So far, so good. Let's continue. Next thing we're going to do is we're going to differentiate dv with respect to time, dv dt. Remember, related rates are always differentiating with respect to time. So let's differentiate this. This is the power rule. We have an exponent of 3 here. It gets multiplied out in front. That gives us an answer of pi times 16 over 100 times h squared dh dt. Why? Because remember, we're differentiating with respect to time. So always dh dt. Don't forget that last part. A lot of people forget that, and it gets you a wrong answer. Okay, so the last step is inserting our numbers in and then using algebra to solve this. So let's do that maybe in purple. So dv dt you already have. We got that number, so let's underline it over here. dv dt, the same dv dt I have over here, is equal to 2 feet cubed per minute. So 2 is equal to pi, that doesn't change, times 16 over 100 times h squared. H is 5, so h squared is 25, and times the h dt. Okay, the last step is solving for dh dt. Again, this is an algebraic step, and we'll be done with the problem. So 2 is equal to pi, and in this case we're going to have the 16 goes on top, and the 25 and the 100 cancel. It leaves me a 4 on the bottom, dh dt. Right, so 25 over 100 is equal to 1 over 4. Okay, let's simplify a little bit more. 2 is equal to pi times 16 over 4 is 4, dh dt. And the final step, let's put dh dt on this side. dh dt is equal to 1 over 2 pi. And don't forget the last part, we also need units. So this is the change in height. So height is changing by feet per minute. The final answer we have for this problem is right over here. dh dt is equal to 1. Sloppy 1, let's erase that and make it nicer. 1 over 2 pi feet per minute. I hope you enjoyed and understood this lesson. Thank you for tuning in.